In the last sessions, I explained gamma functions. In this session, I'd like to explain the Riemann Zeta functions. Riemann Zeta functions is defined with these formulas. Is an infinite series is a 1 over n to the s. So we are going to prove zeta 2. So this means it becomes 1 over n squares. N is go to the 1 to the infinities. Also zeta 4. So this becomes infinite series 1 over n to the 4th. N is 1 to the infinity. To discover these values, we have to be familiar with the trigonometric Fourier series. So let's review the Fourier series. So x is confined minus pi to the pi. So in these situations, any functions can be expressed with the trigonometric functions. So this equation a sub 0 over 2 plus sum n equal 1 to the infinities. So a sub n cosine nx plus b sub n sine nx. The coefficient of the a and b is obtained. A sub n can be calculated 1 over pi minus pi to the pi fx cosine nx dx. Also you can calculate b sub n. It's 1 over pi minus pi to the pi fx sine nx dx. So this is the Fourier series expansions. So we use this Fourier series to expand some functions. First of all, we'd like to consider fx equal x squared. So in these situations, a sub 0 can be calculated 1 over pi minus pi x squared dx. So it becomes 2 over 3 pi squared. And the a sub n, we can calculate 1 over pi minus pi x squared cosine nx dx. Then you can perform the integral. This is a even functions. This is even function. Then it becomes 2 over pi. And the limit is lower limit is changing 0 to the pi, because even functions you can multiply twice. Nx dx. Then integration by part. Two over pi x squared over n sine nx 0 pi minus 2 over n 0 pi x sine nx dx. And the first term, actually if you substitute pi, sine n pi is 0. And the substitute 0, sine 0 is 0. So this first term is 0. Then again, we need to make an integration by part one more times for the second terms. Integration by part. This is minus 4 over n pi. Integration by part. Minus x over n. Cosine nx 0 pi plus 1 over n 0 pi cosine nx dx. So you can write on this ways. Then if you substitute the cosine pi n, it becomes minus 1 to the n. This becomes 4 over n squares minus 1 to the n, because this term is going to be 0. And also we'd like to calculate b sub n. This is 1 over pi minus pi x squares sine nx dx. But x square is even functions. Sine x is odd functions. So product of the even function and odd function becomes odd functions. Odd function is integrate minus pi to the pi. It becomes 0. So Bn is 0. I'd like to write down the one more times for the Fourier series. A sub 0 over 2. N is 1 to the infinities. A sub n cosine nx plus b sub n sine nx. And then you can substitute all the values. So fx is x squares. A sub 0 is a 2 pi square over 3. So this is pi square over 3. And the b sub n is 0. A sub n we have n equal 1 to the infinities. This is 4 minus 1 to the n over n square cosine nx. So we have these formulas for the trigonometric expansions of the x squares. Then you can substitute x equal pi in the both sides. So this becomes pi squares equal pi square over 3 plus n equal 1 to the infinities. This is 4 minus 1 to the n squares cosine n pi. So this part is minus 1 to the n. So this becomes 1. From this equation you can find this part. Sigma n equal 1 to the infinities. 1 over n squares equal 1 over 6 pi squares. So this is actually zeta 2. So I have proved the important formula for the zeta 2. Okay, then I'd like to explain the zeta 4. To find the zeta 4, we use the fx, consider the fx is x to the 4. Then you can use the same type of the calculation to find a sub 0. 1 over pi minus pi to the pi x to the 4th dx. So this becomes 2 over 5 pi to the 4th. So a sub n 1 over pi minus pi x to the 4th cosine nx dx. So I skip the how to calculate, but using the integration by part. Several times. So answer, I just write down the answers. 8 pi squared over n squared minus 1 to the n minus 48 over n to the fourth minus 1 to the n. This is a sub n. And the b sub n, as I explained, it becomes 0 because fx is even functions. And if you multiply the sine function is odd functions. So it becomes 0. So finally, we have equations. X to the fourth equal 1 over 5 pi to the fourth plus n equal 1 to the infinities. This is 8 pi squared over n squared minus 48 over n to the fourth minus 1 to the n cosine nx. Okay, we have already this is a trigonometric Fourier series of the x to the fourth. Then you can substitute x equal pi. So this becomes pi to the fourth. This is 1 over 5 pi to the fourth plus 8 pi squared. This becomes n equal 1 to the infinities. 1 over n squared minus 48 n equal 1 to the infinities. 1 over n to the fourth. So I have just proved this becomes 1 over 6 pi squared. So from these equations, you can discover n is 1 to the infinities. 1 over n to the fourth becomes pi to the fourth over 90. Actually, this is zeta 4. Okay, we are going to use this zeta 4 for the future lectures. So I explained the Riemann Zeta functions. Okay, this is the end of this session.